We may or may not have noticed that when we looked at binomial distributions and compared them to normal distributions, we may have seen some similarities. In fact, before we dig into this, here's a binomial distribution with n equals 25 and p equals 0.5. So what that may mean is that maybe we have 25 people, and the probability that any one person likes apples is 50%. And this describes the probability distribution of, well, how many people are, and the probability of them liking apples. So the probability of 12 or 13 people liking apples is the highest, namely because on average, 50% of 25 will be about 12 and a half. And so that is kind of the average or expected value. So you can kind of think about the mean as being in the center of this distribution. And not only that, but this particular one appears to be pretty symmetric and bell-shaped. So in fact, if I divide it about its mean, if I take it and break it up down the center like this, we can kind of see the symmetry. Now that isn't true for all binomial distributions, but when it seems like the bigger n gets, we probably notice this. Whereas if you look at a normal distribution, it also has its mean right down the center. If you split it in half, this is a distribution with mean 100 and standard deviation 10. Remember, the bigger that sigma gets, the more kind of flat peak and spread out this normal distribution looks. And the smaller that sigma, the kind of the tighter and taller this distribution takes on, because the area underneath there needs to be 1. So there must be some sort of connection, and let's explore that in more detail here. The binomial distribution, though, is a discrete probability distribution. Discrete means there are no data points between any two adjacent data points. So if we have a random variable that is distributed as a binomial with n trials and probability of success on each trial equal to p, then the random variable can take on values from 0 all the way up to n. So in our case of this being 25 people and the probability of liking an apple is 50%, then we could have 0 people liking apples, 1 person liking apples, all the way up to 25, all 25 people liking apples. Of course, not every one of those outcomes is equally likely, but those are all possibilities. And we've established that the mean is n times p. So if you have 25 people and each person has a 50% chance of liking apples, then the average would be 12 and a half people we would expect to like apples. The standard deviation comes out to this funky value here, the square root of n times p times q. Let's recall that p is the probability of success, so p plus q has to equal 1 because either something happens or it doesn't, and therefore q is simply 1 minus p. Now that is, again, a discrete distribution, but suppose that we're not measuring how many people, but we're measuring maybe our measurement x is a person's height. And that height, so we can say that between 22, let's say, or 65 and 66 inches, there are really infinitely many heights between those. You could have 65.5 or 65.273, but there's no way to have 1.7 students, unless that's an average. Okay, so this is just an example of one of those binomial distributions, and we can look at different n. We could make this n smaller. We could even change this probability. And as I mentioned, this is not completely symmetric, but it is symmetric-ish. However, the smaller I make that, we start to get kind of some weird-looking skews and things like that. However, if I make n large enough, maybe this extra 0 in there will take a moment to process. But even there, you can see that it starts to, because there are 2,501 bars, 1 for 0, and then 1 for 1, 2, 3, 4, 5, all the way up to 2,500. You can see that that is pretty symmetric, even though that probability is small. Let's go back to 250 for a second here and make this 0.5. Well, you see we get something that's very, very symmetric and bell-shaped. If I make that something even bigger, like 600, you get a much cleaner approximation. And it almost looks continuous now, right? Because there are enough values to where it's not infinitely many, but it's closer to infinitely many than it was before. Now let's look at the normal distribution. So the normal distribution also has a mean and standard deviation. Every distribution does. It has, well, what's the expected value that you get? And then what is the expected size of the deviation? The way we compute the mean for a data set that is assumed to be continuous is we add up the values and we divide by the number of values. Because we collect one value per person or one value per observation, we sum those up, we divide by n, that's how we get our mean. The reason we can't do that up here is because not every outcome between 0 and n is equally likely, right? If there's a 50% chance of a person liking apples and there are 25 people, then 5 people liking apples is not going to be the same likelihood as, here's 5 people as 12 people liking apples. And the standard deviation is computed by adding together all of the deviations, and I forgot that square root there, so I had to put in my square root. Otherwise, if I didn't have the square root, that would be called variance. And so we're going to add up we're going to find the distance between each value and its mean, and we're going to square that. The reason we square is because it takes care of those negative signs that would otherwise cause the deviations to add up to 0. So we square them, we average them out, and then we take the square root of that to kind of undo the squaring process. And you notice that even that both of those involve a square root. Not that that means that there's a connection, but they kind of, are related in that way. And we say that a normal random variable is called x is distributed normally with mean, mu, and sigma. So all you need to be able to draw that distribution is the mean and standard deviation. Back up here, we just needed to know how many values were possible and what's the probability of success, and then we could build this, and we could figure out the height of each of these bars by computing the probability that x is equal to some one of those particular values is computed by taking n choose x times p to the x power and q, which is 1 minus p to the n minus x power. Okay, so that's how we would compute the probability. So if I wanted to know what's the probability that x equals 12, well, then I would take 25 combination 12, it's the number of ways that could happen, times 0.5 to the 12 times 1 minus 0.5, which is also 0.5, to the 25 minus 12, which would be 13. Okay, so that's how I would compute those probabilities. These probabilities have to be done using an area, and so we use a calculator for it. That is, x can take on infinitely many values, right? Between any two values, like with heights, we said there are infinitely many choices for them. So we get what's called a continuous distribution. And notice there's no separation between 90 and, say, 95, because anything between 90 and 95 is possible. But back up here, between, say, 10 and 11, there's nothing possible. There's just 10 and then there's 11. So this bar looks at the likelihood of getting exactly 10 successes out of 25 trials, or 10 people liking apples. What's the probability of that out of 25 people? Okay, great. So what's the relationship? Well, as that n became larger, a binomial distribution starts to look a lot like a normal distribution as n becomes larger. Now, even if the value of p was really small, as we saw here, if I make that value of p really small, then it looks a little bit less like a normal distribution. You can kind of see a little bit of a skew this way, that it kind of just drops off here and then it kind of tapers a little bit more slowly. But if I make n greater, regardless of the value of p, you can see that at 900 this looks more. I mean, there's still a tiny bit of a skew there, but with 900 it looks a lot better than it did with 650. Okay, well, what does that mean as n approaches infinity? Well, in theory, that if n was infinity, then a binomial distribution would be exactly a normal distribution. But we'll make this more specific. We can use a normal distribution calculator if, and these are kind of rules of thumb, if n times p is bigger than 5 and n times q is also bigger than 5. So in other words, if your average, your expected value is at least 5, and then n times 1 minus p, if that's also at least, or bigger than 5, I should say, then you can use a normal distribution to do that approximation. So let's try this out. Let's see how we would actually do it, and let's see if we get a similar answer. Okay, so suppose 500 college students are sampled. The probability that a student drinks coffee is assumed to be 70%, independent of any other student. Compare the probability that, in other words, between 325 and 340 students in our sample drink coffee. Okay, so we want to know what's the probability that in this group of 500 we end up with between 325 and 340 students responding, hey, yes, I like coffee. And the random variable, capital X, is the number of students that drink coffee. So we know, first of all, going back to the idea of defining this random variable, that although not likely, 0 students could report liking coffee. Maybe we get a really strange sample, and even though there's a high likelihood that people like coffee, that we don't get any. 1 student out of 500 could report liking coffee, all the way up to 500. All 500 might report liking coffee, which again is not as likely because not everybody is assumed to like coffee. Okay, so how do we know, first of all, that if we're going to use the binomial distribution, that this is a binomial random variable? Well, a few things have to hold. One, there are 500 trials. Right? The trials are the students in this case. So there's a fixed number of trials. Fixed number, so that's required for a binomial distribution to be used. Secondly, the probability of success that a student likes coffee is p equals 0.5. 0.7. Which is fixed, right? This is for each student. Fixed probability of success. And also then the third condition is met, that the students are, each trial is independent. Each student drinks coffee independently of every other student. So we have independent trials. Okay, so that these are in parentheses. I'm writing the general requirements, and then this is how in this problem we meet the requirements. So in this case, independent trials, there are 500 students. Those are our trials, and what we're saying here is that the likelihood that Joe drinks coffee is not going to be changed by knowing that Frank drinks coffee, for example. Okay, so we've met the criteria of using the binomial distribution. So what do we want to know? Well, we want to know the probability that between 325 and 340 students drink coffee. We could also get our mean, which we don't necessarily need, but I'm going to go ahead and compute this here. In our case, n is 500, p is 0.5, which is 250, which, by the way, hey, you know, for us to be able to use an approximation, that number should be greater than 5. I'm sorry, it's not 0.5, it's 0.7. I don't know why I keep saying that. 500 times 0.7, which comes out to 350. So we would expect that around 350 students on average out of 500 would report drinking coffee, but this is still bigger than 5. So that means that so far we would be able to use a normal approximation. And also 500 times 1 minus 0.7, which is 500 times 0.3, which that should also be bigger than 5, which it is. That's 150, which is bigger than 5. So this just means that the normal approximation should be close. Okay, so let's actually compute this. What is under the binomial distribution? What is that the probability that between 325 and 340 students drink coffee? Okay, let's come over here and change this to 500 students. Probability of success of drinking coffee in this case. Again, remember, success is not success like it's necessarily a good thing. It just is, it's just a term describing what it is that we're studying, okay? And the probability of between 325 and 340 students, which is already entered in here, we want this option selected. We want the interval between 325 and 340. We should actually be able to come down here and see the highlighting occurring between 325 and 340. We want the sum of all those bars. Now keep in mind, we would have to compute 325, 326, that's 16 different computations that we would need to calculate in order to do this by hand. Keep that in mind. We get 0.1697. So this comes out to 0.1697. So there's about a 17% chance that we collect this data, we ask the students, do you drink coffee? The likelihood that between 325 and 340 of them said, yes, I do like coffee, there's about a 17% chance that that happens. Okay, now let's do part B. Okay, so we've met the conditions. Conditions met. We should always check these before doing this, and we've met the conditions right up here. Let's star this. And now we still want to compute the probability that between 325 and 340 students report drinking coffee out of the 500. But how are we going to do this? Because now X is approximately normally distributed with mean, mu, and standard deviation sigma. We need to know those values in order to be able to plot this normal distribution. Well, hey, wait a minute. This is going to be the same mean as for our approximation is going to involve the mean of the binomial distribution, which is 500 times 0.7, which is 350. So we're going to use 350 for mu, and for the sigma, for the normal distribution approximation, we're going to use the square root of n times p times q. So we're using the quantities from the binomial distribution. So this will be 500 times 0.7 times 0.3, and that comes out to about 10.25. Okay, so that's going to be the sigma that we use. So 350 and 10.25. So let's come over here. We'll do 350 and 10.25. Okay, and again, we want to compute. So that is based on our n and our p and our q. And the probability, I've already had that input here, between, on the interval, 325 to 340, which is just this area here, comes out to 0.1573. This is equal to 0.1573. And compare these two values. Look at this versus this. And they are close, right? They are close. So we're off by about a percentage point, a little bit more than a percentage point. We're off by about 1.24 percentage points. But nonetheless, it does give us a reasonable approximation. And we can kind of check also, we look at these two distributions, right? They're not the same size and shape because we're kind of looking at different things. We can see that that segment right there is, this segment is approximating it. Let's try some different values here and see if we still would get similar results. Let's say the probability between 340 and say 360 students. What would that probability be? Well, on the normal distribution, we would get 0.6707. Let's see what it would actually be, because this is a binomial random variable. It's not continuous. We get 0.6945 as the exact value. 0.6707 is the approximation with the normal distribution. So again, we approximate it to reasonable accuracy or precision. So why would we do this then if we don't get the exact result? Wouldn't it be better just to use the binomial? In a nutshell, yes, it would. The reason normal distributions were often used historically for approximations of the binomial distribution is due to the fact that it being easier to compute normal probabilities. You have to compute an area, a single area. But when n gets very large, the number of discrete probabilities is, there's n plus 1 bars in that distribution, right? So from 0 all the way up to 360, I'm sorry, not 360, up to 500, there's 501 bars. And to compute these probabilities, notice that that requires, from 340 to 360, that's going to require 21 bars, one for 340, and then count up to 360 would give you 20 more. That's going to require 21 computations. So to do this, you would have to do this manually, you'd have to compute the probability that x equals 325, plus the probability that x equals 326, plus all the way up to the probability that x equals 340 for this computation down here. We can see that's expensive. That's a lot of work. Although our probability calculator could do that without a problem, it didn't take very much time at all. But if you were doing this manually back in the past, you would have to manually compute these probabilities, sum them together to get this 0.1697. This, you could actually find just the area between two regions, which would actually be done via the use of a table or an integral table, which we're not going to get into here. But here's the thing, approximations are great, but nowadays computers are powerful and approximations are often not necessary. We can get things pretty much as exact as we want. Unless there's a very specific reason, we won't talk about those here, why you would need to approximate, it is usually better to get exact probabilities. So when working with binomial random variables, we ideally like to stick with the binomial distribution. So that's just kind of my input on that process. Why get an approximation if it's not going to take you any more time? And with technology the way it is, it really doesn't. So now we have this link between binomial, which is a discrete random variable distribution, and the normal distribution, which is a continuous random variable distribution.